In this video, we will discuss the synthesis of lanosterol from tryptophan squalene. This synthesis uses the enzyme squalene oxidase, which is a monooxygenase. And among its properties, we will say that it's very specific because the molecule of squalene contains 24 carbons long and it has 6 carbon-carbon double bonds, and it's only doing the epoxidation of carbon number 2. Another important fact is that this enzyme needs the use of a coenzyme FAD. We have seen FAD, the flavin dinucleotide, as an electron carrier used in metabolism, specifically in the beta oxidation of lipids. But in this case, it will be to bind the oxygen that will be donated to the carbon-carbon double bond number 2. In this process, we would form an epoxide. We know that epoxides are easy to open up because they have a 3-member ring that has very small overlap of hybridization of sp3 carbons and oxygen. The molecule of squalene, as we have mentioned before, is synthesized from the joining of 2 molecules of farnesyl, the 15 carbons long molecule, to make the tryptophan squalene. The first step of the synthesis is the epoxidation of carbon number 2, the carbon-carbon double bond between carbon 2 and 3. In this epoxidation, we said before that is using the molecule of FAD as the oxygen donor, and it will also do the protonation of the epoxide to trigger the ring opening. During the ring opening, we can generate a secondary carbocation if we add the OH to carbon number 2, or the tertiary carbocation if we add the OH to carbon number 3. And in this case, this is the most stable for the synthesis. If we continue with that synthesis, we will say that first step is the epoxidation of carbon number 2. Then we will protonate the oxygen that will trigger the ring opening. And after that, we will have the cascade of the carbocations. And that is, if we rearrange this molecule, because we have freedom of rotation around single bond, we will see that these bonds are not as far as they look like over here. But then from carbon number 6, 7 double bond, we are going to form a brand new bond that is making the first 6-member ring. But at the same time, that is going to generate a brand new carbocation on carbon number 6. So now carbon number 7 is the one that is closing a brand new ring. And now this carbocation cascade will continue with the addition of the 2 electrons from carbon number 11, 10, double bond, to form a new ring. And that will be, as is shown in here, you are generating a brand new carbocation on carbon number 10. So we will see here that this one will become a carbocation, closing a second ring. And then on the cascade, from carbon number 14, 15, we are going to close the third ring, and so on until the point. So we see that the cascade of formation of rings will happen, and that's happening fast. But once we get the carbocation on carbon number 19, then we will start with the hydride shifts and methyl shifts. I believe that we discussed a little bit of that today during the WebEx. So we will say that we are going to shift this hydride. When we shift the first hydride, then we're going to shift a second hydride unit to generate a carbocation on carbon number, what's this number? 14, on carbon number 14. So on carbon number 14, we are generating a brand new carbocation that is going to help us now to do the methyl shift. So methyl from carbon 15 will shift to 14. Then we're going to shift and I have that for the next page, make sure that is understood. So we will say on the next page that after the first hydride shift, we have one hydride shift, second hydride shift. Now we have generated the carbocation on carbon number 14, and that's going to trigger the two methyl shifts. So from carbon number 15 to 14, and then from carbon number 10 to 15. So we have two methyl shifts. So we started with one methyl here. Now we have methyl on carbon number 14 and 15. 14 and 15 now have the methyl. And now we have a carbocation on carbon number 10. We need to lose a hydrogen plus, that's a hydrogen alone. So that is going to now help us to form a carbon-carbon double bond. And that is the molecule of lanosterol. And lanosterol is the precursor, and we have that mechanism again. This is what we are following. I know that in your textbook you have it with the chair conformation, which is more difficult to follow, and I wanted to present you that in writing. And also I have the same mechanism, but this is using my biochemistry textbook, because I mentioned today that oxygen is being bound, is being carried by an FAD molecule, but in other sources we also find that NAD is also able to carry the oxygen for the epoxidation in the formation of the squalene epoxide. And now we have, after the epoxidation, it's the same exact cascade, so you guys can see that you are just breaking a double bond. When I break this double bond, I'm making a brand new bond. Now I'm going to generate the carbocation on this carbon number 11. I'm going to do the same until the point that we have the protosterol cation. So that is the one that will trigger the hydride shift and methyl shift. So those two is after we produce this carbocation. And then after that is the elimination of this hydrogen. So we are going to eliminate this hydrogen to produce the carbon-carbon double bond. I wanted you guys to see it from a different drawing, because this is the one that I'm following as the McMurray from 1992. But now we see the same reaction. So if we overview, and this is the picture that I provided to you guys, if we see an overview, we have learned that those equivalent to isoprene dimethyl allyl pyrophosphate and isopentenyl pyrophosphate will combine to make the geranyl pyrophosphate, that is a 10 carbon unit terpene, is the terpene, and we have the 15 carbon units that is called the farnesyl pyrophosphate. Two molecules, 2 units of that one will make the squalene, and from the squalene we go through the epoxidation of carbon number 2. That's the first thing. After the epoxidation, we are going to protonate it, generate the cascade of carbocation. So you see from here you start making a brand new carbocation. We have done that one. Then we see a brand new carbocation, and then another carbocation until we end on the open chain. So there is carbon number, I believe is 18 or 19, I believe. Okay, so from this point now we have the hydride shift. First hydride, we move that one up, then this one down. Then we will have after that, you see, first hydride shift, second hydride shift, then methyl shift, second methyl shift, and then we're going to lose a molecule of oxygen. And the most important thing is to remind you the importance of this reaction, and that has to do with the lanosterol is the precursor of cholesterol, and from cholesterol we can obtain all other steroids. So from here I'm going to show you just what we have. Yes, from Lanosterol will produce cholesterol, and cholesterol we know is the precursor of all other steroids. During the lecture in WebEx today, I told you that we have the methyl groups, all of them in one side, and we all, from the many steps, you will see that one side of cholesterol is totally hydrophobic, and the other side is also hydrophobic, but it has the branches. More than that, from cholesterol, we're going to do some chopping, some oxidations. We're going to cleave to produce the sex hormones. And just remember that now we have more functionality. But if you observe clearly, the functional groups where you can have molecular interaction as being hydrophilic side, and then you have hydrophobic side. You have a ketone on one side and alkene. So more modifications can happen. So we can have, this is the male and females. And this one have to do with, in some cases, regulation of glucose intake. You have an aldehyde group, a ketone, and alcohol. But observe this one. But in particular, I want to spend a little more time just to remind you the molecule of bile salt. This is cholic acid. And that is of importance. The bile contains bile acids and cholesterol, and they are very important in metabolism because these molecules have a hydrophilic side, which is going to be this one where you have all of the OHs. I presented you this in two different ways. So you see the OH carboxylate, they are on the same side, so they can produce droplets of I will say the lipids will be surrounded, the hydrophobic part by that side, and this part will be surrounded by molecules of water. So the structure have a meaning. It's important how the structure is being made. And then the last thing is, why do we care so much about cholesterol? So for digestion of, first because it's the precursor of the synthesis of all other steroids. And second, because we also have that in the digestion, we will see that we have all of the hydrophilic part in one side, hydrophobic part on another. But one more is because cholesterol is part of the cell membranes. And we say in the membrane, you have the phospholipids, heads and tails, and then you will have the cholesterol units that can help us, because cholesterol units, oh my goodness, are going to be distributed in such a way that they can interact with the hydrophobic tails. But we are going to say that this molecule is fairly flat, but it can interact with these hydrophobic tails, disrupting accumulation, let's say cluster of increasing, I will say, the membrane fluidity.